Infrared radiation is a mechanical force. When a photon strikes matter, it interacts directly with the molecular architecture, driving chemical bonds into violent oscillation. For analytical chemistry, we operate strictly within the window between 4,000 and 400 reciprocal centimeters. But for this energy transfer to occur, a rigid physical prerequisite must be met. The molecule must possess a dynamic, fluctuating electric dipole moment as it vibrates. Symmetrical molecules, like nitrogen, fail this test. With no shifting dipole, an IR photon passes straight through without transferring energy. Conversely, a polar bond has distinct partial charges. The photon's electric field couples with these, physically pushing and pulling the atoms to vibrate. This coupling only succeeds if the frequency of the incoming photon exactly matches the natural vibrational frequency of the chemical bond. An infrared spectrum, therefore, maps the dynamic electrical fluctuations occurring across a molecule's architecture. This strict dipole requirement explains a persistent paradox in spectroscopy: why certain extremely strong chemical bonds fail to register on an IR spectrometer. This image shows the structural formulas of ethylene on the left and bromoethylene on the right. In the perfectly symmetrical ethylene molecule, the carbon-carbon double bond stretches and compresses mechanically. However, because the molecule is perfectly symmetrical, the opposing vectors of electron density cancel each other out. The net dipole remains zero. But substituting a single hydrogen for an electronegative bromine atom shatters that symmetry. As the bond stretches, the center of electron density shifts. This generates a measurable change in the dipole moment, resulting in strong infrared absorbance. A missing peak on an IR spectrum does not guarantee a missing bond. It indicates a localized chemical environment existing in perfect symmetry. To predict exactly where a bond will absorb, we model the chemical bond using classical physics. A covalent bond behaves exactly like two masses connected by a mechanical spring. Hooke's law calculates natural frequency based on two variables: the spring's force constant, K, and reduced mass, mu. Heavier atoms possess greater inertia, slowing oscillation to absorb lower energy photons. Inversely, double and triple bonds act as stiffer springs, vibrating faster to absorb at higher wave numbers. Classical stretching along the axis of the bond is only one type of movement. The atomic architecture also undergoes complex bending deformations. This diagram illustrates the specific normal modes of molecular vibration. While the primary axis stretches, the surrounding atoms undergo simultaneous scissoring, rocking, wagging, and twisting motions, each absorbing at distinct frequencies. Classical mechanics elegantly predicts the frequency at which a bond should vibrate, based on mass and stiffness. However, it fails to explain the rules governing how these bonds absorb discrete packets of energy. At the atomic scale, the classical spring model breaks down. A macroscopic spring can accept any arbitrary amount of continuous energy, but molecular bonds operate under quantum constraints. This harmonic oscillator graph shows strictly quantized, evenly spaced vibrational energy levels. The bottom V equals 0 state sits above the minimum, meaning even at absolute zero, a molecule never stops vibrating. Furthermore, an absorbing molecule can jump exactly one energy level at a time. The massive, dominant fundamental bands seen in a typical infrared spectrum are almost entirely the result of the vast population of molecules jumping from the V equals 0 ground state to the V equals 1 first excited state. Absorption is a binary event. A bond receives a photon carrying the exact required quantum of energy to bridge the gap between these specific V states, or it ignores the photon entirely. The ideal harmonic oscillator contains a physical flaw. It assumes a bond can be stretched infinitely without breaking. This plot contrasts the ideal harmonic oscillator with an anharmonic oscillator curve. Real bonds have limits. Excessive stretching causes atoms to fly apart at the dissociation limit plateau. Approaching dissociation, anharmonicity forces the higher quantum energy levels to crowd progressively closer together. This physical deviation from the ideal spring relaxes the strict quantum selection rules. The system will occasionally permit forbidden jumps of 2 or 3 energy levels simultaneously. These forbidden multi-level jumps are called overtones. Because the higher energy states are crowded closer together, these overtones appear in the IR spectrum as distinct, much weaker peaks at slightly less than double or triple the frequency of the fundamental band. The structural imperfections of real molecular bonds produce these overtone and combination bands. They transform a few sterile mathematical lines into the complex, rich fingerprint unique to every chemical structure. An isolated vibrating bond is a theoretical fiction. Gas phase molecules are simultaneously tumbling and rotating rapidly through space. This diagram illustrates transitions between rotational levels. Each vibrational state contains tightly packed rotational levels. During a vibrational jump, rotational quantum number J must change by positive or negative 1. J decreasing creates the lower frequency P branch, while J increasing creates the higher frequency R branch. What appears conceptually as a single transition is actually a dense forest of simultaneous vibrational rotational microevents. We can observe this theoretical line coupling directly in the physical output of a high-resolution spectrophotometer. This methyl bromide graph displays percent transmission across the wave number range, manifesting a distinct triple dip pattern. The sharp central dip around 1305 reciprocal centimeters is the Q branch, occurring only in specific geometries where a pure vibrational transition without rotational change is allowed. Analytical chemists rarely observe these precise rotational branches. Routine analysis is almost always performed on liquid or solid samples, not gases. In condensed phases, molecules are packed tightly. Rapid, continuous molecular collisions physically disrupt the rotational states, smearing the pristine fine structure into the broad, continuous absorption bands typical of organic chemistry. Within these condensed environments, inductive effects from electronegative neighbors or hydrogen bonding subtly alter the force constant of the bond, shifting the exact wave number of the peak. An infrared spectrum bridges classical mechanics and quantum theory. It is a direct readout of atomic masses, spring-like force constants, and strictly governed quantum transitions, all perfectly encoded in a beam of invisible light.